For a flow over a flat plate that stays in the laminar regime for the entire length of the plate, or the transition happens in the close to the rear edge of the end of the plate, then we use the coefficients for the laminar flow. So let's say if we have laminar flow over the entire plate, let's say for x over L between 1 and 0 we stay on the laminar, or when the transition from laminar to turbulent happens the last portion, like 5% close to the really leading edge. So let's say if this is the plate, either everything remains in the laminar or the transition happens here. And we can find out where the transitions happen, this xc from Reynolds number of x and c times 5. If you replace the properties here, we can find out the location where the transition happens here. If that happens, then we use the Nusselt number L as we saw before, 0.664, Reynolds number L power half, Prandtl number to the power of 1/3. Now, if we have turbulent flow, over the entire plate, so assuming everything is turbulent, then the Nusselt number, the average one, is going to be 0.037, Reynolds number L to the power of 4/5, Prandtl to the power of 1/3. So these are the two conditions when everything either considered laminar or turbulent, but it's quite often that we have both of them. Like initially we have development of laminar flow, and after that we have the turbulent flow, or for cases where we have both laminar and turbulent flows, or transition from laminar to turbulent happen, let's say at x0 less than 0.95. So when we have this plate, what happens initially, we have a laminar, we have a transition, and then we have a turbulent flow. So this is laminar boundary layer, and this is turbulent boundary layer. Then for the first part, what we would consider is we would get h from the laminar. So we're gonna use hx of laminar. And for the other part, we are gonna use h of x of turbulent. And we can get the average of HL, which is going to be 1/L integral of 0 to xc to the transition point. And for the first part, we are going to use the hx laminar for the part that is laminar dx plus integral of, let's say, xc to L hx of turbulent dx. So we can do that. Now, if we replace the definition of convectivity transfer for laminar and turbulent, and we do the integration and change that one to the Nusselt number. So Nusselt number of L, which is average HL, L over K, is going to be 0.037 Reynolds number L to the power of 1/4 minus a value called A, Prandtl 1/3, where A, it depends on the critical Reynolds number, which is 0.037, Reynolds number evaluated at the point XC. to the power of 5 over 4 minus 0.664. Reynolds number evaluated at xc to the power of half. Now for a flat plate, as we discussed, this critical Reynolds number is 5 times 10 to the power 5. If you replace that, A is going to be 871. Therefore, the Nusselt number L for a flat plate, if you have a mix of them, is going to be 0.037 Reynolds air to the power of 5 over 4 minus 871 Prandtl to the power of 1/3. And this equation, we are going to have mixed laminar and turbulent boundary layer over the plate, and Reynolds number is going to be 10 to the power of 8 greater than 5 times 10 to the power of 5, and Prandtl will be less than 50 greater than 0.6.